right here with vision, PDIF, and motion profiling really deserves 3 longer than 1 hour sessions. So this is going to go quick, and you're not going to get all the information you absolutely need, but hopefully it starts the conversation and gets you the resources so you can go to that next step. My name is Corey Applegate. I'm the mentor for the Granitecitygearheads 3244. I'm going on my 4th year as a mentor. I've worked 21 years as an electronic controls technician over at Electrolux. Last year I was a beta tester for the Limelight vision system, which we will talk about a little bit right here. And this year I am also beta testing the Java VS Code stuff. Today with me here doing the second half.
My name's Brandon. Was a student in FRC for 1 year in 2016. Been a mentor for 3 years. This is my 2nd year CSAing. I specialize in LabVIEW. I've also done beta testing for the past 2 years. Computer science student at the University of Minnesota Duluth.
So we do definitely want questions here, but we're going to go quick here because I know his session is going to take likely the longest. So we're going to go right off the bat. Vision's for the rookie. If you're new to vision, I'm going to give you 2. Well, that's coming up here a little bit. So when we start talking about vision in FRC, we'll start looking at cameras from cheap to the relatively expensive. We're going to start out with like the Pixie Camera, relatively cheap. There are a few of you have it. It talks over serial, I believe, to the RoboReel, sending data over. JVOS, which I have one around here somewhere. Another inexpensive camera. I've started playing with it about 4 weeks before I got my first Limelight. I have abandoned it. I never looked at it again.
For that.
USB. That's what most of you guys are probably familiar with. Is plugging a USB camera into your RoboReel and just getting a driver point of view to start using for drive control. But you can also start doing some vision pipelining in your RoboReel in other locations. We'll talk about that in a little bit. IP cameras, I don't have one here. It's in the pit. Some of the Access IP cameras. Again, they're starting to get a little bit more expensive. There you're going to have an IP address where a coprocessor can pick it up and start doing some vision pipelining, or you can just feed it to a web dashboard for a drive control. Then we can start getting into a cell phone where you start having cheesy vision. You hear that vision out there. They have a really decent library for using an actual cell phone mounted on your robot. The vision pipeline's right in there. It's got some nice tuning tools on there. I did play with that a little bit too. Got the Limelight, abandoned that. This is going to become a Limelight infomercial a little bit on that. Then we get into Limelight, which last year was $399. That's mounted up here. It's upside down right now. It's kind of an all-in-one vision system. It's a coprocessor light camera. You can control the light on and off.
Last one I had on there was Coprocessors. This guy will probably run you. This is multiple pieces, so you can get away with it. Probably about $900. Spendy.
Is that the KTX and stuff in there? Or is that
Up Squared. It's from Europe.
Other coprocessors would be like even a Raspberry Pi, a Kangaroo mini PC, which is on our robot in the pit area.
Jetson TX1 or whatever the new one.
Common systems we kind of talked about is that USB on the RoboReel, coprocessors, where you're going to need IP cameras, USB cameras. All-in-one systems are going to be that Limelight and the Android phone, the cheesy vision. 2 of the easiest options when new to vision. The first thing I'm going to tell you, if you're not familiar with Screen Steps Live, go visit there. Inside, down there, you're going to start seeing vision for FRC. There's some great tutorials on there, and towards the bottom, you'll see a section about Grip. Grip is a downloadable application, Java application, that you can start very inexpensively with the hardware you have. You already have a USB camera. You can start doing vision tuning right now, start adjusting your HSV values. Their tutorial is really great, and I'll have a picture of that on the next slide. Disadvantage of using Grip, though. Drag and drop into the timeline, so it's picture-oriented. Disadvantage, extra hardware you're going to need to mount a light on your robot. You're going to need to mount a camera on your robot. You might have to mount a coprocessor. So you got lots of different components you're going to have to mount on your robot. As well as you're going to have to, it will export the code that you can copy into your robot program. You're going to have to wire in the images into that code and take the data out of there and use it. So there's going to be some extra coding that's happening there. The Limelight side of it, it is a little bit expensive up front at $399 last year. I don't know what the new ones are going to be out, but I have heard that the version 2s will be out before kickoff. The beta testing is starting next week. Again, it's all in one. You bring in one wire. You can go up to one wire. It does PoE, so you bring your Ethernet cable with your injected PoE power on there. and you mount it two locations on the bolts. If you look at that guy, there's just 2 bolts in there. It's one and done. The light and everything there. The light and everything. It has a really nice web interface. We'll take a look at. Grip. And then if you do experiment with the grip pipeline utility is supposed to be supported. I haven't seen it yet. I'll be getting it really shortly. You'll be able to export the grip pipeline, so you can do a really custom pipeline. You can export it into the Limelight and it will on it as well. Disadvantages. Cost is really the biggest disadvantage you can possibly. And actually, if you start looking at all your coprocessors and stuff like that, the costs are really equal, if not maybe even a bit cheaper. And your development time. You can get a vision processor up and running 15-20 minutes and be pretty accurate on tracking your targets. And any adjustments you need to do, it's on the web interface right on the robot. So here's what grip would kind of look like up here in the upper right-hand corner. What grip stands for is graphically representative image processing. It uses that GUI to develop your pipelines down there. It can run out directly on any coprocessor. We had a little mini Kangaroo coprocessor mounted on a robot during Steamworks. It did all of our boiler tracking for us. As well as you could take the image and run it on your driver station if you have a powerful enough driver station. And it generates or you can output the pipeline like we talked about, put in your code. Where to use the grip, then we say that image is coming back to your driver station likely anyhow. If you have a powerful enough driver station where you're not worried about too much latency with your joystick controls because you don't want to interfere with your robot control, you can run grip directly on your driver station and send that information that's back over to the robot over network tables. Mini PC, as we talked about, it exports that open CV pipeline. You can put on a RoboReel, Raspberry Pi, more. But the disadvantage there again, you have to know how to capture the image on the RoboReel, take that captured image in a mat, push it into their pipeline. There's a lot of coding and work that has to be done there. The Limelight, and I'll show you the web interface here in a second. Fast, all-in-one solution, camera, coprocessor, light, pipeline tuning, all in one wire over with PoE. You can have up to 4 pre-programmed pipelines on the ready where you can select it at the driver station and say if you need to check the boiler, you need to check the PEG, you need to check some other goal. If there's multiple different goals on the field, you can with a button or with your program say run pipeline 1, run pipeline 2, run pipeline 3, and they're all able to switch over to those different pipelines. So they're all selectable. You can also plug in an auxiliary USB camera onto it, so you'll have 2 camera feeds coming back to your driver station stitched together. One will be what the vision process is doing. The other one's will be that USB, which you could use for a driver camera. Also through network tables, though, you can take the Limelight and say, I don't want to use this as a vision processing camera. Flip the camera mode to drive mode, and it automatically puts all the adjusters into drive mode, so you can use the camera as a normal forward-looking camera. When you're ready, when you need a pipeline, shut it back to vision mode. You're back to vision mode using network tables. Here's what that browser looks like, and I actually have it pulled up here. You want to grab a vision target over there? Yep. Hang it towards the ceiling. So that's kind of one side. We're kind of happy, unfortunately. Alrighty. That image right there is an image of the boiler. There you go. It's not finding anything right now, but you can see right now it's running pipeline 0, stronghold. If I go over here, and I'm not sure which one it is, that's the cube. There's the boiler. You can see right there it's finding the boiler right now. So it's been tuned to find 2 objects, make a contour of those 2 objects, and start doing a crosshair. If you see that crosshair is floating around in that blue box, and then there's one stable in the middle. Let's just say right now we're shooting fuel into our robot, and this is exactly where we want our robot to set. After we go through all the thresholding and tuning, we can look at that a little bit here. We go to output, and we can calibrate the crosshair. Now coming back here at the top, you see that TX at -0 degrees. Limelight sends back degrees from target, not pixels on screen. It says we are 2 degrees off. So now once we calibrate it, it said this is where we want our robot always to be, and it's returning 0. Any variance of that, it's going to start returning degrees from target. And then your input system right here, you can start adjusting your exposures.
I can get that back up there for you if you want to.
Nope, no, that's fine. I'm going to go to raw image here. Now we're looking at the raw image. Lots of sliders. And grip, you can do all these same kind of sliders as well, but you're going to have to stitch your pipeline together. I believe. Any quick questions up to this point? Yes.
When you say degrees, is that, does it like know the different distance or?
So what it is, what you're going to have to do with a USB camera is you're going to have to know your resolution, like 320 by 240. And you're going to have to know the field of view of your camera, say 56 degrees. And now if you have a pixel anywhere on that, you can now extrapolate how many degrees from center is using those pixels, dividing the pixels by the total. Grip already in its process background is already doing all that for us because it knows its field of view, and it's just returning back to network tables degrees from target. So it's taking care of all that coding in the background for us. Anything else? So, in kind of a conclusion, there are many different systems out there our FRC teams implement, but there are no right answers. Start simple, remove as many variables as you can using that grip. The tutorial on there, the Screen Sets Live, absolutely is the first step to do, is to use a webcam. Be successful with that before moving on to more complicated things. That's why you get in the limelight, have a successful vision process, get it working, and now if you want to know why, now start kind of backwards engineer it a little bit and say, can I reproduce this with some of this other hardware that we got? So we're going to kind of move into PID, a little bit overview of that if there's no more revision things. All right. This is going to be half of me, and I'm going to lead into his part right here. So PID, if I had this question before, what does PID and then the F factor stand for? PID is proportional, integral, derivative, feed forward. I kind of simplified it. Proportional is the relative error from where you're trying to get to from where you're at. Integral, what happens there is if you're trying to get to a set point and you can't quite get there, you start adding a little bit of integral to your PID controller, and that will help close that gap. It's error over time. Derivative, if you see always blow by your set point and come back and you have a lot of oscillation, you can add tune a lot of that out with your P factor, but you need all that. You can put some derivative in there, and that's kind of a damper, hold things back. And feed forward, a lot of times when we do flywheels, and anything that uses velocity, we'll do a feed forward. What percentage of power do we need to apply to this motor to give it full output or a target output? Open loop. I want to go 300 RPM. I want 75%. Just that's off the bat to get us there. And then the PID comes in there and starts correcting the error in there. It just gets us there quicker. Couple places we can use our controllers is directly on the robo reels. There are PID subsystems and PID controllers. If we get out of hand with that, we can use our digital I/O, our motors coming in there, and but we can start to eat up a lot of our CPU. We do have limited resources in there. We may want to go off and do something other. If we're doing our vision on there and PID, you're going to see your CPU usage on the robot start to spike, and you're going to have some latency problems. The other option is on the motor controllers. A lot of the Talon SRXs. There's a new DMC 60C. I haven't actually experienced it a little bit, but some of the very preliminary documentation says that's going to have that same COM port on it that is going to be compatible with SRX line of encoders. And then the Spark Max. That's a new controller that has that brushless DC motor. If you're using the brushless DC motor, you will not be able to use the encoder port on there. They apparently use the same pins. So if you use the Spark, as I understand it, I haven't read everything on it, but chatted that you can use it as a brushed motor controller, and then you can use that port. On the robo reel, you're going to start seeing some real simple proportional, not even a PID controller on the left there. You may have in your X2. Calculate the error, target minus value. Figure out what the command value is going to be. Take the error, multiply by some constant P, and then set your motor to that P. So it's kind of a really simple proportional command. And actually with the Limelight, there's a lot of tutorials on there. The Limelight you can use directly as your feedback device for tracking targets. You don't have to get the degrees from target, now go find a gyro and close your error, then go check the target again and see where you need to go to. You can go directly, and I have some examples of that sometime if you want to talk more about that. Otherwise, you got a PID subsystem and PID commands. I did highlight this, and it'll be in the next slide, this live window add get PID controller. What that does is gets you, cancel, I want to see that. This little box right here, this gives you a little PID tuner. So we can go into test mode on our robot, and we can set points of our PID control system and enable it and adjust our P. So if I enable the robot, in test mode. It went to 0. I'm going to go to 45 degrees. I can't hit enter because that'll disable the robot. If I put this P to 1, really hot,
it's searching. It's too hot. So now I can start tuning this down to figure out 0.1. And so like we start moving back. This tools have been created by just writing that one line of code for test mode to start tuning in our PID. Tuning PID is probably one of the scariest things at first to get into. With that one line of code, tuning PID, this is on the robo reel side. It's very simple.
The next step,
and I believe on the slide, I'm going to take my 2 minutes here. It's on you.
I just showed that
right there.
On the motor control.
On the motor
Really,
control.
I'm going to
point you over to Crossroad Electronics.
In their documentation,
and here's some links here. And
there's a slip up here to grab. These links are on there too about our presentations and some more information. They have really good tutorials in your language of choice, LabVIEW, C++, Java, on how to tune their motor controller for velocity, position, and even some motion magic, which is a really awesome, simple motion profiling, which he's going to lead into right here. Their motion profiling tutorial is a little less awesome. But motor controller, you're going to actually control the amount of slope at the beginning, amount of slope at the end, and how fast you're going to cruise along there. With a basic PID controller, if you have a long ways to go, it's going to slam the power on. Your motor's going to turn on instant full power and slow down when you get there. With motion magic and other profiling, you can control the acceleration rate and then cruise along and control the deceleration rate as well. So with that, any quick questions on there? I'm going to turn it over to Brandon here. No? All right, thank you.
HDMI. Perfect. All right, so we're going to get started here. Warning, any Java code that you see in this, I do not guarantee will work, nor is it going to work because I don't code robots in Java. Everybody here uses Java, and I was told, hey, put a shot out there, try to write some Java code. Please do not take this character by character, try to put it in your robot and come back to me saying, why isn't this working? Well, here's your warning, it will not. It gets the process across. We code in LabVIEW.
That's going to be seeing your working demo in LabVIEW.
But I have written Java to try to correspond with what we're doing in LabVIEW.
And translate it over.
Yeah. So what is motion profiling? Has anyone heard of Team 254? Just a couple? So it's a vector-based driving path that your robot will follow during autonomous. Got a little video from their finals match in Houston, finals number two. Their human player did a really good job of recording their auto. You get a nice side view of it right here. You're gonna notice how smooth the robot moves, how it accelerates and turns. That's what motion profiling is. You get good at motion profiling like this, you're starting the game 4 cubes up on the other team, and it's disgusting what you can do. They have become really good at it, and they made motion profiling pretty much what it is today. This is what happens when you get motion profiling up and running. We're a rookie team. We're down there at the bottom. 254 is just running the show. So why it is important for my auto is it's very accurate. You can have curved paths, it's faster, and your development time is extremely short once you get that initial phase done. So the hardware needed for this, you need 2 SRXs, 1 for each side. I would recommend Crossroad Electronics encoders. You can use other encoders. I would personally recommend Cross the Road. That's plug it in, pretty much works all the time, really good encoders. And then for any other motors on your drivetrain, it has to have the ability to slave to your Talon SRX. Victor SPXs work great for this, half the price, a little bit smaller. You can slave Talons to it. Doesn't matter, it has one of those two. I don't know if Spark's gonna have that ability on it, but the SRX and the SPX both do. So what is in a path? The path is a series of points that your motor controller follows across the field. It has your encoder distance, it has velocity, and it has your acceleration. There's going to be one for the right side and one for the left side. This is something called Vanica Path Generator. This is a third-party application that someone has gracefully put out on GitHub that you can make your paths in. If you see here, this is a right starting position to the left scale. You can see what the robot is going to drive before you even put the code on the robot. You can take this, it runs off of something called Jackie's Path Planner, Jackie's Motion Profiling, whatever you want to call it. If you've seen it before, she's put a lot of work into it. There's a new version coming out. She's done a great job with it. It works for everything that we need to do in the FRC environment. You're going to have a time step in there. We're going to use 0.05 seconds. You'll realize why a little bit later in the PowerPoint, but please use 0.05 seconds. Velocity, it's your max velocity of the path. If your robot can go 10 feet per second, set your max velocity to something a little bit lower than that. Set it to, say, 8. You don't want to max it out just because you don't know what your battery power is going to be. Acceleration is the max. Your robot can accelerate from, I would say, a stop position to any given speed. We usually do about half of what your velocity is, even maybe a little bit less, so it's a little bit smoother. Jerk, use 60. It's the derivative of acceleration in respect to time, to a lot of physics. Everybody's physics-based here. You can maybe go calculate that yourself for your robot. We found 60 to be a good number. Wheelbase, your width, whatever your width of your robot is. That one right there is 2 feet exactly. From
Center point of each wheel?
Center point of each wheel, yep. Center point of right wheel to center point of left wheel is 2 feet exactly. So you're going to notice here for that path that I showed, for this path right here, you're going to see we have this graph that's associated with it. Might be a little small for you guys to read, but red is left trajectory and orange is right trajectory. This is the speed of your motors at that given time during autonomous. You can see that each one, we have a left-hand turn coming through here. So our right wheel is going to speed up faster and our left wheel is going to slow down, so it makes that turn. All that is already written for you with Jackie's Path Planner. Really nice, really easy to use. So that graph shows just visual of what's going on and what your motors will be doing during
Creating that
autonomous.
pathfinder, you're kind of dragging waypoints.
Yep, and I got-
you got that coming up?
Yep, I got an example of this right here. Here's that one I was showing a little earlier. So we're just going to delete all the points. And we're going to make it real easy. We're going to start here. So I'm just going to click. We're going to work our way here. Maybe we'll go to here. Let's work our way maybe to this point right here. We're going to change that last point to 90 degrees. So it makes a little bit of a turn. And you can see kind of the path goes a little bit out. So I don't like that. We're going to drop it down on the Y scale by 1. So we're going to drop that to 21. Made that curve a little bit smoother. We're going to come over to here again. It'll say an invalid point, but we change this to 90 degrees to match the other one. Comes through here. That's how you build a path. That's how you build an auto. It's that easy. So we're going to go back into the presentation here. This year for the beta, I talked about it a little bit in the last session, session 4 with the other CSAs, but there's something called Pathweaver. This is put out by WPI Robotics, written in Java. You just run a build on it, and it comes up like this.
It'll be automatically
Yep.
installed with your VS
Yep,
Code installed.
it'll be right in there when you install the libraries for the year. You just say, I'm gonna go, let's run Pathweaver, and it'll pull this up for you. Currently, at its state, it's very hard to use, and it took me 45 minutes to draw this. You saw how quick it took me to do it in the other program. Don't be alarmed, it's still in beta, and since I've written this presentation, it has gotten about 1,000 times better, and I've yet to have it crash on me within the last week. It's gotten really good. For Java teams, this, in my opinion, is going to be your option, because this will go and push right into your Java code. You don't have to do any file manipulation. We'll be going over that a little bit later. Java and C++ teams, I'd probably recommend this Pathweaver to you. As long as they keep everything going at the speed they're doing, it'll work really well for you guys. So now we're going to look at the files here. You're going to see up here at the top, you have MP_left, MP_left detailed, your preferences, and then MP right and MP right underscore detailed. The left and the right, those are your two sides of your drivetrain. And you're going to have two versions of each file, one detailed, one not detailed. We use the not detailed one. And it's going to look something like this when you open it up in Excel. The files are in a .csv format, which raw looks like this to a computer. It's comma separated by values. Column 1 is your encoder distance for that given time step. Column 2 is your velocity. Column 3 is your duration in milliseconds that you want that given point to run within your SRX. So what do we do with these files, and how do we get them in and actually use them with the SRX? You're going to have to upload them to the RoboRio. You must have an admin account with a password. That has changed this year. I'd recommend FileZilla. You can log in with 172.22.11.2. Username is admin, password is blank, and you can drop a whole folder right in there. The web-based configuration utility is now gone for the year. They have replaced that. If you went to the beta, you saw a little bit of it. It's replaced with the Phoenix Diagnostics utility. You'll see that a little bit later in the year. You have to put these files into a safe spot. For me and for us, our LabVIEW team, and I know you can probably vouch for this too.
Not yet.
Home, LabVIEW users, National Instruments, bin, data. Your program will never overwrite that folder. We build a folder inside of there that we call paths, and then from there, we go and put our path names. This example here is drive forward underscore right. You can have left underscore RL, whatever you want to have in there. And then you put in the individual files, which is going to be your left and right side. So down here you see drive forward underscore R, and then the file mp underscore left.csv. That's your file that actually has your data points in it. So when you upload it to the RoboRio, it's going to look something like this. You see we have inside of our paths folders right here. Excuse me, it's on the desktop because I was in Duluth and didn't have a robot with me. Pretend it's on the Rio. You have center, left, center, right, a couple other things. All your different autonomouses are going to have its own individual folder. Now, getting your paths into your code, you have to determine the file location. For us this year, they left the game data in the driver station for next year, so we might have game data, we might not. We don't know yet. We found a good algorithm to be starting position underscore XX. So if we started on the left, underscore switch scale. If we wanted to pass it, not do it, we left an X in there. If we wanted to do it, we put R or L in there, and you can build all your different types of paths through that. For LabVIEW, you're going to have a case structure on here that has each individual file in it. So for your autonomous, this one is left underscore RR. It's going to address the file location, and it's going to go find that on your RoboRio. Your files will be mp underscore left.csv and mp underscore right.csv. For every path, the only thing that changes is the folder that you're going to access. Your auto selector on the dashboard is going to tell you, hey, what do I want to do? Do I want to do switch, scale, both, and where is my starting position? Java, this is how you get in your game data. You can copy this down. I took it off of WPI's website, so I know this one hopefully works. Your Java selector, you can just run a very large case switch structure saying, okay, if we're left underscore XL from what we determined from our game data back here, we're going to name our left path, and that's just a big string that has your file location in it. If you're left underscore XL, same thing, big string with file location. Default, make sure you set your default to do nothing, because if it finds something, or just good practice is to have, if something goes wrong, just sit still. So now we're back to LabVIEW here. We have our file name, which you can see down here, CSV file path. Now we need to actually grab that from the RoboRio. In Java, you grab that, you read the buffer. If the buffer still has data points in it, you're going to keep going and split at the commas. You're going to bring it in. You're going to write it to a new class, motion profiling class. You're probably going to have to build a custom class for this and put in your entry 0, 1, 2, 3. You're probably going to have 3 on there. And then you're going to add that to probably a custom array of your motion profiling class. So what's happening in here is you prompt for your file location, you grab the file from the Rio, it brings it in as one batch file. You run a for loop until that file is empty, grab all my points through it. And what we need to do is we need to convert our points. What the Pathfinder is putting out is a generalized statement. You have to make it unique to your robot. That is done through here. Convert your feet into your encoder ticks. That Pathfinder will output in feet. Your robot determines stuff by encoder tick. So you're just going to run that calculation. And then you also have convert your velocity into your robot terms. Your velocity in feet is different than your velocity in robot encoder ticks. If you don't know how to calculate ticks per rotation on your robot, you could put a little Sharpie mark on your wheel, rotate it once, read what the output is and do that. Or you could do the math if you're using a cross-road encoder. 4096 times your gear reduction, 4096 times 3 times 7 equals 86,016 ticks per rotation. Whichever one you want to do, I'd recommend the math. So, any questions? How many people have I lost?
Yeah, it's got one statement to say that as far as getting files onto the RoboRio, Gradle can be used very easily since everyone's moving to that next year.
Okay.
It's really easy to use that. Every time you do a build, it just moves them over.
Okay, yep, so you can do that. Wherever Gradle will put them, just change that file location to wherever Gradle puts that given file. With LabVIEW, the one problem is since all of them are named the same but are in different folders.
We were looking for your tutorial. So we'll be looking for your tutorial.
Yeah.
When you go to Green Machine, I think we actually have a branch up there with that last year.
Okay.
We used properties files last year, stored them on the Rio and pulled it off on eNet.
Okay. Yeah, no, the LabVIEW portion, if you have the same files, the same name, but different folders, it throws all sorts of errors. So we've learned files that'll you just drop them in one big batch, especially since we lost the File Explorer on the web configuration utility.
The other thing is, Jackie, I don't know if I was going to do, how it's going to play with the newer NI libraries, but she had libraries that did all the file reading and all the conversions for you, so it was just basically ready to give an output to the talents.
Yeah, it was. She had her own Pathfinder. Not only did it make the path, but I think they might have also had a C version of it. I'm not 100% on that, but I know she's mainly Java when she's writing code.
There's something to look at, I think, next year whenever they release documentation. So Jackie's put a lot of stuff into WPID now, so.
Yep, and her link to her Pathfinder is all on here on that handout that we have. It's all on there, so visit her GitHub. She's very knowledgeable. She responds to emails. Don't abuse it, but she does respond to emails. You'll see her on Chief Delphi a lot too. Any other questions, comments? Alrighty, we'll keep going. So we have our path made. Path's been brought into our auto routine, and it's something the SRX can recognize. We're going to look at the SRX software now that you need to do. What is assumed is you have your SRX set up in brake mode. You've given it a reference name, whether that be left master, right master, whatever you want to name it, something that you can address it by. You have your PIDF set up, just like Corey went over. I'm going to show you how to calculate F here real quick, but P, I'll show you how to also tune that. You do not have to use I and D for motion profiling. You've also set up your quad encoders, and you've zeroed them at the start of autonomous. If you have quad encoders, or if you have any encoders, or any sensors, it's good to zero it at the start of autonomous. Here's an example of the talent setup inside of LabVIEW. We're opening this talent in CAN slot 12. We're setting its reference to left master. This, we just set it to a % output. We're overriding it to brake mode, set the sensor phase to false, configure the sensor to the quad encoder, set our quad position to 0, configure our PIDF, and we're selecting our motion slot 0. That's a LabVIEW example. This Talon example through Java, I pulled off of Crossroad Electronics GitHub. Should be right. I don't know if I grabbed everything I needed to, but the same thing. You're setting your PIDF. You're setting up your encoders. You're zeroing them. You're setting them to brake mode, giving them a reference. A lot of you guys should know how to do a good majority of that right now, and there might be a couple other things. Again, Crossroad has great documentation on getting all that set up.
Great tutorials. Yeah.
So your feed forward gain is calculated based on your drivetrain. You take your % output, you multiply it by 1023, and you divide it by your velocity. So an example is 100% times 1023 divided by the velocity that we acquired off of this robot gives us a feed forward term of 0.025, yada, yada, yada. Your proportional term is going to be calculated. You're going to run a 10-foot path forward and backwards. If it's not getting to the 10-foot mark, increase your P. If it's overshooting your 10-foot marks on each end, decrease your P. That's it. P, and it's pretty forgiving with motion profiling. You do have a pretty large range, but try to make it tuned relatively well. So now we are into autonomous. You're going to grab your references. So for us, it's left master, right master, left slave, and right slave. You're going to set your motion frame period at 25 milliseconds. This is why I said put your timestamp at 0.05. This is going to be half of what your timestamp was. There's also more reasons why we use 0.05. We'll get to those even later. You're going to clear your motion profile. At the start of autonomous, it should be empty. Just as good practice. Clear it again. You don't know what was laying around there from the last guy that touched the robot. You're going to set your trajectory point duration. Your offset is going to be 0. You want points to run back to back to back. And you want to remember to do this for your left master and your right master. You're doing this for both motors. Java, there's a little snippet of code. Change the frame period to 25, clear the trajectory, configure the time period to 0. So step 3, you're going to check to see if your buffer is full. The reason that we have a 0.05 time step in our motion profile is the Talon buffers can handle 300 points. And if you do the math, 15 seconds at 0.05 second time steps puts us at 300 points. The buffer will never be full. You'll never have to clear the buffer. It makes your life as a programmer a lot simpler.
You won't have to stream points to the buffer.
Mm,
Yeah.
huh?
Streaming points to the buffer. Yeah.
Yep. And so we're going to grab the cursor from the class. What you need to do is you need to keep track how many times that for loop went through your program to figure out what point you're actually on. You're going to push the position, velocity, and duration onto the queue with the cursor index that you have from your for loop. So through this whole entire class, this cursor coming right through here is just doing a +1 every time it runs through. It's grabbing the array index element with that cursor ID. It sends duration, position, and velocity. And then it'll set a 0 position in invert motors, which is false and false. Java, here's a little bit of that. See if I can read this for you. So it selects the slot. It's running a for loop up here. It's calculating we'll go back here. Your position, velocity, sending it into the different slots, and checking to see if it's the last point or if it's a 0 point. And then at the very end of that for loop, every time it goes through, it's going to push it onto the stack. Step 4 is you set your motion profile you set your motors to motion profiling. This is done with that for loop. So if you look at that for loop that I had before, and I showed in our program too, it runs through the entire autonomous. Then you're going to slave your follower to your master. And then once you get there, your robot is driving using motion profiling. So this is integrating your manipulators with that new path that your robot's now driving. It compares the time you've ran
I'm just gonna close it a
that
little
given
bit.
subsystem, and it synchronizes it with the SRX buffer. So to tell time, if your initial time is 31,200, this is here. Once it enters that for loop that's pushing all those trajectories, it is now have an active timer over there. It's going to do some subtraction. We're going to divide by 50, and remember, integer division, decimals dropped. We come out with an answer of 3 for this given one. Why is that number important? Well, what we did with that clock there is now that number that's getting output from our clock comparison and doing the division by 50, that now corresponds with lines in our .csv file. So not we converted it to being Talon friendly, we're converting our time to now be friendly to us. So now it's back in our hands, and we can figure out what line of the program or what line of the CSV file is my robot running. I took a little snippet just from a auto code that's doing a left starting position to a right scale. And if you see here from 92 to 96, you see that this is my encoder distance, but my velocity is 0. This tells me I'm stopped somewhere. If I go and look at my path and figure out where it is, it tells me I'm stopped at the scale. So what I can determine from this is before I get to 92, that arm needs to be up at scale height. From 92 to 96, I need to shoot the cube out, and at 97 or beyond, I can put that arm back down. This maximizes what you're doing with your robot down to the 0.05 second time step. You can be very efficient with what you do. Again, I just explained this. 0 to 97, I gotta get to the scale height. 92 to 96, I can shoot the cube. 97 to X, I need to go to the floor level. And 97 to whatever the next point is, I need to run my intake in. So what we're doing in here too is just an if statement. If I'm between 150 and 300, export true. And you can see we have different Boolean lines going out. You can put a couple if statements in there, or maybe a switch statement, whatever you want to do. What that tells me is I can use a state machine here having multiple Boolean values to tell me what I need to do. It'll take that Boolean value and convert it to an enum, or just whatever you want to do. Maybe convert it to a string, whatever you want to do. And I can now determine what I need to do with that given portion of code. So if you see over here, if this one's false, it's going to be reserved. If it's true, it's going to be switch. And you just have an order of precedence as you go through. If you write your code, one should not override the other, but it does have a little bit of fallback on that. And it'll just send it into a switch statement. It'll tell me what I need to run my manipulators. Here's an example of this robot running an auto. This was over the summer before it got its new paint job. So it just drives forward, turns right, comes over, drives back. We didn't have our timings right on our arm, lifts the arm up, shoots a cube, drops back down, and gets ready to intake the next cube. If we had our timings right there, obviously we could be stopped at the scale for under a second and shot the cube, and we can go to the next one. Autonomous was huge this year. Autonomous will probably be huge next year, considering WPI is making a path-finding path maker. Really focus on the autos. They probably, in my opinion, are going to put a rank point with it too, just like they did this last year. It's something that you can make. If you put a little bit of time into it, it does take time to develop, but once you make it, auto development becomes super easy. I'm going to pull up just a little portion of code here. So if we pull up our autonomous here, I got this bottom section disabled. So this is our manipulators. Here's all the different paths that we run. If we go into any given one, so say we say center underscore left, you can see all I have to do inside of the program is just change the time that I call my stuff. Up here, we're grabbing our path and say, I want to grab center underscore left. Okay, we're going to go to that all the way down to the path folder. We're going to find the center underscore left folder, and we're going to grab our 2 CSV files out of it. We very rarely have to touch the autocode to make paths. All we have to do is pop into here, draw something new, upload it to the RoboRio. It's very easy to manipulate your paths. Or say you are off by 2 feet to the right. You can go, we can move. Oh yeah, you're gonna complain about that. We can go move these points. If we need to go 2 feet to the right, we're just gonna change this X to a 21. Change that X to a 21, change that X to a 21. You just move 2 feet to the right, going behind the cubes. Yep. 254, yep.
You show the blade back and forth between it. Are you able to run it out to go back and forth?
With the one that Jackie is coming out here within a week or two, you will be able to, is what she has said.
Each one of those is like a separate path.
You want to
So
say the
if
question
you're
again for
looking-
the mic? I don't know. I didn't quite hear the question. What was his question?
Whether you can go, when the cheese poops are going back and forth, whether we can do
Add a
that.
reverse to it.
Yeah, currently, we do it by hand. We have macros on our computers that will just switch paths for us, and then we can just put them together. Jackie has said on GitHub that she has added the reverse function in there. I don't know if that's going to let you do those back and forth paths, or if it'll just reverse a path and you just have to stitch them
So when you get to
together.
point 90, do you just pause your motion profile and to do your thing, and then you can reinitialize motion profile and to continue on 90, 92, 93, 94?
So what we do, I can pull up a file here. We go to
Or do you just fire off a new motion profile?
So we keep running the same one, and what we do, this one does not have it.
Oh, just put your velocity at 0, put your position at this common position and along a 2-minute.
What'd you say?
You just negate rows.
So what you do is, if you want to drive forward and backwards, you have to start from your last given encoder. So if we look down here, you can see that we stop right here. This is where we stop. You negate your velocity, subtract from your encoder ticks, and flip the right and left.
And you just do that manually.
We do it manually. We just made macros on all our computers that we can just, we copy and paste them over, and then we have macros that'll just do all that for us.
The cheesy poof, their multi-cube auto like that, they generated a trajectory for each one of those steps is how they did it. So they would use the same type of state machine that he was talking about to say, okay, we're now going back to get another cube. And so they would have a path just for that one.
And if I go back in my folders here, there's one folder in here that says path segments. These are all the different, to go from point to point to point. So if I grab a marker here and just draw a very crude FRC field. Something like this. So path 1, say you start here, you're going to go for like a double scale or something. You come here, you're gonna come in here, and this is where you stop. This is path 1. If we go back into our file here, path 1 would end right where this first 0 is at the top. And we added some more zeros and brought the encoder, the same encoder down so that we could pause there. We could do something. And then path 2 starts. You can see my velocity is negative, and if you look, my encoder ticks are going down. Well, that's because we're going the other way. Path 2 goes from here down to here. Path 3 goes from here to here. Path 4 goes from here to here. 5 goes to here. 6 goes to here. 7 goes to here.
The path existed in different files, or you have them stringed all, you manually strung them all together?
You build them independently, and then we've manually strung them all together.
There it is.
If you're tech savvy, you probably could write a program to string them together for you, if you have the time and would like to do that. Yep.
So last year everything was deterministic. You know, things didn't move around.
Yep.
If a lot of years you would have to engage vision and jiggle around.
Yep.
Which is going to change all your positions. How would you accommodate for that?
Pathfinder, we've gotten paths to be within about 0.5 inches and within about 2 degrees of each other. We have not found a real need for vision. If you saw the cheesy poofs, they didn't use vision for that path. It's if you tune it well enough and it's running fast enough and you got it down enough, you really don't have to pair vision with it.
The only thing like the cheesy poofs did for like their last cube,
Was-
they knew they might be off a little bit, they would open their arm up to go and try and get a cube. That was the only change. They even had code that physically could detect the presence of a cube, but in their autonomous, they never used it once. It was just pure paths and
Yep, that was all their 7-8 year development of motion profiling, their custom thing that they've completely excelled at, and they'll just keep using year after year. The only vision they used during autonomous was they had a camera at the driver's station to determine the height of the scale, so they didn't have to go all the way up every time. They're like, we'll just go up just enough and then keep going. Any other questions? Yep. Yeah. Is what?
Reverses the town SRX motion profile.
Yeah, so it will generate reverse paths. The new one that is coming out. She hasn't, it's in beta right now. It hasn't gone full public and she hasn't put her stamp of approval on it yet. But it will, she said hopefully this season. I trust her. She's good about timelines and stuff like that, so. Are you Java, C, or LabVIEW? Use Pathweaver.
Over here?
It uses the same back end stuff. Yep. Yeah, it still uses Jackie stuff in the back end.
How do you do the calculations again for the .csv file?
The calculations inside of the .csv?
Yeah.
Like how do those numbers get generated, or?
The Pathweaver software exports this code into a CSV file. That is the resulting export of the.
I have generated none of those numbers. Those were all given to me by a different program.
In the maroon?
Yeah. So between Jack and Capital and all those, what do you recommend for LabVIEW usage?
LabVIEW, it's whichever one you feel more comfortable building paths in. For LabVIEW teams, it really doesn't matter. You could use the Pathweaver, or you could use the Vanik motion profiling generator. At this given point, I like the Vanik one better. But also, the Pathweaver is not done yet. So whichever you prefer, whichever you can build.
A lot of the
paths
links we
with,
talked about are on here. One thing I didn't mention is when you go to the Talon SRX's tutorials, they have a lot of formulas for calculating your P, your I, and your D. I actually created a Excel spreadsheet, Google Sheets, where you can start plugging plug into the green cells the numbers that it's asking for. It'll all port in the yellow cells the calculations. So if you can look at their formulas, and you can use this Excel spreadsheet as well to plug in your numbers and have it and spit out the values.
Anything else? Any other questions? No? Alrighty. If you have any questions in the future, contact, I know, the MNCSA page.
We'll be here cleaning up for
yeah.
a few minutes, so if you have a few that you want to just bring up to the front here as individual questions, you're welcome to. I hope you enjoyed your day at Jumpstart today. I hope you all learned something new, and we'll look forward to you next year. Thank you.